This is the introduction to section 2.1, patterns and inductive reasoning. Okay, our objective here is to use inductive reasoning to make conjectures, and there's two vocabulary words: inductive reasoning and conjectures, and we're going to talk about those. Okay, so what is inductive reasoning? Okay, inductive reasoning is reasoning based on patterns that you observe. So essentially, it's more or less a conclusion based on things that you observe in patterns that you can end up concluding. Okay, you observe patterns in some number sequences and some sequences of geometric figures to discover relationships. There are certain relationships that happens because of that. Okay, so let's look at a lot. What's going to happen in this section is you're going to look at a lot of examples of patterns and see if you can conclude what your next few numbers are, and also decide what's happening in each sequence. So, for example, let's take a look at letter A. Okay, letter A. Okay, so in letter A, we go from 3 to 9 to 27 to 81, and we want to figure out what the next two numbers would be. Okay, so we got to figure out how is it going from 3 to 9 to 27. Well, if you look here, you wouldn't. Let's see. If we go 3 to 9, if we added 6 to get to 9. And then we would add 18 to get to 27. Well, that isn't going to work because that's not the same. Okay? So maybe we look at multiplication. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. Now we notice we have a pattern. We're multiplying by 3 on each one here. So here we're multiplying by 3. Okay? So now if I look at my next two numbers, 81 times 3, that would be 243. And then 243 times 3 would be 729. Those would be my next two numbers in the sequence. Okay, so that's how you're kind of looking for these patterns. Let's take a look at letter B now. As you look at letter B, you notice you have a circle with a triangle in it, or a circle with a three-sided figure. Then you have a circle with a square in it, which is a circle with a four-sided figure. And then you have a circle with a pentagon in it, or a circle with a five-sided figure. So as you look at this, you notice your figure is going up by one side each time. So my next two would be a circle. Put a circle down here. And then if I put a six-sided figure in here, so it would look something like this vaguely. Okay? Be a circle with a six-sided figure. And then you would have a circle with a seven-sided figure. And if you were to do that, it would look, there's 1 and 2 and 3 and 4 and 5 and 6 and 7. That's not the greatest, but you can tell that there's 7 sides of that figure. The next one would be 8, the next one would be 9, so forth and so on. Okay, so that's what you're looking here on, trying to figure out on these patterns. Okay, so you may want to find the 10th or the 100th term in a sequence. In this case, rather than finding every previous term, you can look for a pattern and make what we call a conjecture. A conjecture is a conclusion you reach by using inductive reasoning. Okay, so it's a conclusion that you end up saying, okay, if I'm multiplying by 3, I know that my 10th term might be 15 or whatever it might be. Okay, so what are the next two terms in each sequence? What I want you to do on these is I want you to be able to figure out these next two terms before class tomorrow. See if you can figure out what they would be and tell me, especially in letter A, what's happening in each one of these. Okay, so let's look at the bottom here. And it says, what conjecture can you make about the 21st term? Now, let's talk about these terms. Okay, this is term 1, the R. Term 2 would be the W. Term 3 would be the B, so forth and so on. Okay, so this in this case right here, this is term 1, 2, 3, 4, 5, 6. And you'll notice it's going RWB, RWB. So there's essentially 3 letters here. Okay, and we want to know on the 21st term what it would be. Okay, so the 21st term, You'll notice you have 21 terms. If I divide them by 3, that means that the seventh time it's going to happen. Okay? So, as you look here, we go to 3. You notice the letter B is at 3. The 21st term, 7 times, it's going to end up being a letter B because every third term is a B, and 21 divided by 3 terms is 7. So it's going to end up being perfectly on the letter B. That's a conjecture. You were able to make a conclusion from the information that you had there. Okay, so let's continue here again. Looking at the circles, what conjecture can you make, or what conclusion can you make about the number of regions 20 diameters forms? Now, a diameter goes all the way across the circle. So, as you look here at this example, okay, as you look at this, you'll notice this is one diameter in here, and that breaks it into 2 parts. This one has 2 diameters, 2 lines that go all the way across the circle, and that breaks it into 4 parts. This one has 3 diameters, and that breaks it into 6 parts. So for 20 diameters, we want to know how many parts there will be. Well, if you notice, if you look, these here, they're doubling every time. So for 1 diameter, there's 2 parts. 2 times 2 is 4. 3 times 2 is 6. So for 20 diameters, if I take and multiply that by 2, that's going to give me 40 parts, or 40 regions. Okay? So you're able to conclude that from that information. Now, not all conjectures turn out to be true. You always want to test your conjecture with multiple times. So you can prove that a conjecture is false by finding a counterexample. Okay, by finding a counterexample. Now, a counterexample is an example that shows a conjecture is incorrect. Okay, so as we're looking at this, now you're going to make a conjecture and decide, okay, from this conjecture, is there a possibility that this could not be true? Okay, so finding a counterexample. What is a counterexample for each conjecture? So, if a name of a month starts with the letter J, it has to be, or it's a summer month. Is that true or false? Well, in this case, this is false. I need to find a counterexample. Well, my counterexample is the month of January. That's a winter month. So now I've proven that conjecture to be false. Okay? The second one, you can connect any 3 points to form a triangle. Well, that's true. I put 3 points like so. Draw a triangle. There's my triangle. I got to find a counterexample that shows that that's false. Well, if I connect 3 points this way, is that a triangle? No, it's not. That's a line. So now I've proven that that conjecture is not true. When you multiply a number by 2, the product is greater than the original number. So let's put a couple examples down. 4 times 2, that's 8. Well, in this case, 8's greater than 4. If I put 5 times 2, that's 10. Well, 10 is greater than 5, not 4. Okay. Let's try this number. Let's take negative 4 times 2. That gives me negative 8. Is negative 8 greater than negative 4? No. This is my counterexample. That's false. Negative 8 is not greater than negative 4. In this case, okay, it's true for positive numbers, but it's not true for negative numbers. Okay? So, let's take, and what I want you to do is I want you to find some counterexamples for these 3 questions before class tomorrow. Okay? So, find some counterexamples. Also, don't forget to complete your WSQ on section 2.1.